Hi everyone, for today's lesson we are going to learn about the qualities of absolute value graphs. Before we get started, let's talk about our learning objectives for today, in which I would like you to be able to say, I can identify the domain and range of an absolute value function, and I can identify the end behavior of an absolute value function. So those are key characteristics that I'm going to need you guys to be able to do. Before we get started, I want you guys to please pause the video and write down some ideas of what you remember about functions and be ready to discuss what your thoughts were the next time I see you. So this is something I would like you to make sure that you do on your own and be prepared for the next class. So I'm going to give that direction to you. So write down anything you remember about functions. And be ready to discuss. All right, so a relation. Relations and functions are related to each other. Now, a relation is simply a mapping. And a mapping can be represented in a table. It can be represented in a graph, ordered pairs. It can be represented with these two ovals where you're seeing it mapped onto one another. It is a mapping or pairing of input values. With output values. It is a mapping or pairing of input values with output values. Typically those input values are like our X values and our output values are our Y values, and we typically express relations as ordered pairs. Now, very special and specific relations are what we call functions. And a function is a relation, or a mapping or a pairing of a set of ordered pairs, in which each input has exactly one output. And I'm going to emphasize the exactly one output. This means that in a function, the X values cannot repeat, and I'm going to put that in quotes, meaning like you see two X values that are the same, but the Y values can repeat. So let me write that nicer. Our domain are our X values, and they represent the set of input values. And our range are our Y values, and they represent the set of output values. And once again, relations and functions can be represented in a table, a set of ordered pairs, a mapping, as well as graphs. And so what we're going to do in this first example is we're going to explore each of these and decide whether or not it's a function, and then identify the domain and range of each. Now, in this table, we have -4, 3, 5, 2, 11, 3, and 22. Do the X values repeat? No, they do not. So because the x values do not repeat, that means every input has exactly one output. So therefore, yes, this is a function. Whenever you're given just a set of ordered pairs and it's not related to any specific equation or graph, that means that the domain is just going to be a set, and I have like a little squiggle right here, of our x values, and we typically write those in numerical order. So our x values are -4, 5, 11, and 20, and I'm going to close that set. My range, well, I do have 3 and 2 and 3 and 2, so the y values repeat, and we know that that is true in a function. Y values can repeat. So writing our range, it's simply going to be 2 and 3. You don't need to write the number that occurs more than once. It just simply is a 2 and a 3. Those are our values that we would see in our range. For the next one, we have 0, 2, 4, 1, and -4, 1. And once again, our x values do not repeat, so therefore, every input has exactly one output, and yes, this is a function. And once again, because it's not related to an equation or a very specific graph, we would write our domain as a set, and our values going in numerical order, we start with -4, since that's the smallest of our x values. We have -4, then 0, then 4, and I'm going to close it with a squiggle. Our range in this case, we have 2 and 1, so I will write that as 1, 2 with squiggles. Now, these squiggles do not represent ordered pairs. They represent a set of values that belong to a specific title, in this case, domain and range. This one's called a mapping, and I know it says pair and solo, but I wanted to just kind of like show you what we're going to be doing for these types of problems. So in this problem, we have ourselves a mapping, and we have input values and output values. And what I want you guys to view this problem as is ordered pairs. So like one ordered pair would be 3 going to 4. So 3, 4 is an ordered pair. And then we have 2 going to, I'm sorry, this is -4. There's a negative on the outside. Then we have 2 going to -4. And then 2 is connected to 5. And then 1 is connected to 5. Now in this problem, our input values repeat. The number 2 has more than one output. So although this is a relation, it is not considered a function. So therefore, no, this is not a function. We can still identify the domain. The domain is going to be all of our values in the input, 1, 2, and 3. And then our range is going to be all of our output values, which are once again 4 and 5. But once again, this is not a function, and that is because the value or the input number of 2 has more than one output. And so because it has more than one output, emphasis on the more than one, this means that it is not a function. All right, let's go ahead and look at some of the graphs. For this problem right here, for letter A, this is a graph that starts and stops. So I would like you guys to please go ahead and put in this point right here at the corner where this graph would actually end. And so whenever you're looking at graphs and determining whether it is a function, you want to look for a thing called the vertical line test. And the vertical line test says that if you can draw a vertical line going through only one point every single time, and there doesn't exist a location on the graph where that graph will cross more than one point, then it passes the vertical line test, meaning that this graph is a function. And in this problem, I can take a pen and go straight across, and I would only go through one point at a time for this, and therefore this graph passes the vertical line test, indicating that yes, this is a function. So whenever we write our domain, because it is on a graph, we wouldn't just list all of the numbers like we did in the previous examples. Instead, what we would do is we would talk about it as a range of values, because this point right here has meaning. I don't know specifically what it is, but I do know that it has meaning. It is a value. So my domain in this problem means that I need to talk about all of the x values that this graph touches, starting at my smallest point and ending at my largest point. This point right here is surrounded by a circle, which means that it is an open circle and not included in our graph. So when it comes to domain and range, I'm just going to look at the x values, and the smallest x value that this function touches is located at 1, 2, 3, -4. So I'm going to write -4 is less than or equal to x, which is less than. The biggest x value that it touches is 1, 2, 3, but because it is an open circle, I'm going to write -4 is less than or equal to x, which is less than 3. It is not included. Or if you wanted to write this in interval notation, we would have a bracket around -4 because it's included, going all the way up to the number 3 and a parenthesis around it because it is not included. It's an open circle. Now looking at the range, I'm only interested in the y values starting at the bottommost number going all the way up to the top. So the lowest point on this graph is located right here, and my y value in this case is at -1. And it is an open circle, so I'm going to say -1 is less than y. And my largest point, or my tallest point, is located at 1, 2, 3, 4, 5. It's located at 5, and because it is a closed circle, I'm going to say -1 is less than y, which is less than or equal to 5. And writing it in interval notation, this is -1, 5 with a bracket around the number 5 because it is included. For letter B, put a point right here. And in this problem, it does pass the vertical line test. I can only draw a vertical line going straight down, and it only crosses one point at a time. So yes, this is a function. And so our domain in this case, it looks like our x values start at our most minimum point is at 1 to -3. And then we have an arrow, which means it's continuing on forever and ever. And so this is an array. And the way that we would express it is we would say that all values of x would be greater than or equal to -3. And to write it in interval notation, we start at -3. That is our most minimum point. And it goes on forever and ever all the way to positive infinity. Our range in this case, we're looking at all of the y values, and it touches nothing all the way up until we reach this point. And my y value at this ordered pair, so it might be helpful to write that ordered pair as -3, 1. My most minimum y value is 1, and then I have an arrow pointing up. So that means that all values of y would be greater than or equal to a +1. Or if we were to write that in interval notation, we would start at 1 and it would go on all the way to infinity. Now, once again, I'm going to remind you, I do not care how you express your domain and range as long as it is accurate and it makes sense. I am very open. I don't even need both each time. I just need one way. For this problem, it's a parabolic function, and it is a function because, once again, the vertical line, if we were to draw a vertical line anywhere on this graph, it would only cross one point at a time. My domain in this case, if we're looking at my x values going from the left and right, I have an arrow pointing to the left and right. So because I have an arrow pointing to the left and an arrow pointing to the right, that indicates that my domain is all real numbers. It doesn't have a starting point or an ending point. You can also express this as going from -infinity to positive infinity, but I think most of us feel pretty comfortable with the all real numbers symbol. Our range, well, we have arrows pointing down, which indicates that it's going all the way down to -infinity, but we have a maximum point, and that maximum point, if we were to look at it, it looks like it's located at 2, 3. So we're only interested in the 3 because this is range and we're looking at our y values. So it looks like it's all values of y that are less than or equal to, because it's pointing down, less than or equal to 3. Or you can view this as our most minimum point is -infinity, going all the way to a +3, and there would be a bracket around it. All right, let's go on to the next page. The next time I see you, what I want you to be able to discuss is sketching graphs of non-functions. What does that look like? What do they have in common? This is going to be something where you will either share out or compare with others, and just make sure that you understand the idea of when something is a function versus when something is not a function. All right, let's go ahead and talk about our next idea, which is end behavior. Now, the end behavior of a graph's function is the behavior of the graph as our x approaches either positive infinity, looking to the right, or negative infinity when you're looking to the left. Do you see an arrow? Do you see a dot? How does the graph end on each side? So our end behavior of linear functions with a positive slope means that if you were to graph or draw in a linear function, a line with positive slope, we would ask ourselves, how does this graph end? As x approaches positive infinity, we see that there is an arrow pointing up. And because there is an arrow pointing up, we would expect our y values, or our function, to approach positive infinity. So the arrows represents the language of approaches. And as x approaches negative infinity, we see that we have an arrow pointing down, which means that our function is approaching negative infinity. If we were to draw in a linear function with negative slope, as x approaches negative infinity, we have an arrow pointing down. That means that our function is approaching negative infinity. And as x approaches negative infinity, our function has an arrow pointing up, indicating that our y values are approaching positive infinity. And that is for linear. Linears or odd functions tend to have end behaviors that are going in opposite directions. So one's going one way, one's going the other way. But when you have like even type functions, absolute values, quadratics, as we will explore, they have different types of end behavior. And if we were to draw in an absolute value function that points up, as x approaches positive infinity, we have an arrow pointing up, indicating that our function is approaching positive infinity. Once again, as our x value approaches negative infinity, we still have an arrow pointing up, and that means our function is approaching positive infinity. And anytime that we are analyzing absolute value functions that are pointing up, you'll see that they're both going to be positive infinities. For an absolute value function that is pointing down, as x approaches positive infinity, we have an arrow pointing down, meaning that f of x, or our function, is approaching negative infinity. And on the other side, as x approaches negative infinity, our function is pointing down, indicating that our function will approach negative infinity. So this idea is something that I need you guys to know and study. It comes back a few times in the next couple of units, so please make sure you understand the language and the meaning between all of the symbols. Let's go ahead and look at example number 3. This is piggybacking off of what we did in the last lesson. It says, for the following examples, graph the function, compare with the parent function, give the domain and range, and describe the end behavior. So in our last lesson, we just compared to the parent function and graphed the function. Now we want to talk about what the domain and range are, and we want to describe the end behavior. All right, here we go. This is an absolute value, and we know that in order to graph an absolute value, you need to know what the vertex is, and remember that it's always the opposite of what you see inside. In this case, it's going to be 1, and exactly what you see on the outside, which is 4. Our a value in this case is -4/3. And let's go ahead and graph. I'm going to plot 1, 4, and then from here my slope is -4/3, so I'm going to go down 4 to the right 3. And I'll reflect that. 1, 2, 3, 4, 1, 2, 3. And I might even be able to keep going. 1, 2, 3, 4, 1, 2, 3. Because you know I like to have multiple points. Anyways, you might need to pause the video to get yourself a straight edge. So I'm going to grab my straight edge. And I'm going to draw my absolute value function. It is beautiful. And now I'm going to describe the transformation as it relates to the parent function. So the first thing that we have here is a negative value. So I'm going to talk about the fact that we have a reflection. The second thing I'm going to talk about is the fact that our A value, the absolute value of A, is 4/3. And 4/3 is kind of tricky because it's a fraction, so we automatically think that it has to be a shrink, but 4/3 is bigger than 1, so it's actually a vertical stretch. And then the third thing we're going to talk about is the translation. So number 1, we have ourselves a reflection across the x-axis. The second thing we're going to talk about is that we have a vertical stretch by a factor of 4/3. And the third thing that we have is a translation, 1 unit to the right and 4 units up. Let's go ahead and talk about the domain and range. In this problem, we have an arrow that's pointing to the left and an arrow that is pointing to the right. Therefore, our domain is all real numbers. Our range in this problem, well, we have arrows pointing down and we have a maximum value. And because we're talking about range, whenever I'm looking at the vertex or the maximum value in this case, I'm only interested in the number 4. And it's all values of y that are less than or equal to 4. Or you can write it in interval notation of negative infinity all the way up to 4 with a parenthesis around the negative infinity and a bracket around 4. When it comes to end behavior, we would write it as x approaches. Now it's always going to be written the exact same way. As x approaches positive infinity, our function, and always call it by whatever name that you're talking about. Don't call it just y or f of x because it sounds nice. Always go back to what the function is called. In this case, it's called g of x. G of x approaches, we have an arrow pointing down, and that is negative infinity. Then as x approaches negative infinity, the other side of the graph, the left side of the graph, g of x approaches, we have an arrow pointing down once again, so it approaches negative infinity. All right, let's go ahead and move on to the next page. These next 2 problems, I would like you guys to please go ahead and try on your own and be ready for discussion. If you want to just wait until I see you next time, that's perfectly fine. But these next 2 problems are your turns or solo problems. The next section, you might need to pause the video and see if you have access to a graphing calculator. So go ahead and pause whatever, do whatever you need to do in order to make sure that you have access to a graphing calculator. You're welcome to use a graphing calculator on a computer, or if you have your own, that might be a good thing. We use a graphing calculator a lot in this class. All right, here we go. I'm going to turn on my graphing calculator, and it says using the graphing calculator to talk about the transformations. So it says to get an absolute value on a graphing calculator, what you're going to do is you're going to press the math button, then you're going to go over to number 1 where it says ABS and a parenthesis. So our math button is located below alpha, so I'm going to press math. I'm going to go all the way over to where it says num, and then I'm going to go to number 1 where it says ABS and a parenthesis. And ABS represents absolute values. Now I have a fancy dancy calculator. You might not have this fancy of a calculator, and it might say ABS and then a parenthesis. You'll have to close your parenthesis if that's what your calculator says. So in this problem, we want to find the requested information about the graph. So what I'm going to do is I'm going to have you guys go to y equals, and then from there, I want you to please enter in -1/2. So you might need to go -0.5 or negative parentheses 1 divided by 2 to say that that's our A value. Then identify our absolute value symbol by pressing math, going to the right where it says num, pressing number 1 or enter for absolute value, and then entering in x plus 4. I'm going to press the right arrow so that I'm outside of the absolute value symbols. Once again, if you have the a different version, you might have to close the parentheses. And then I'm going to write -9. So we're going to actually graph this function. From here, to get a standard window, you'll have to go over to Calc, and then or on the calculator, you'll need to go to Zoom, and then number 6 where it says standard, and standard means that it gives your x and y values going from -10 to +10. And if you can't see the graph, then you might have to go back to window and adjust. So I'm going to go to Zoom, and I'm going to go down to number 6 where it says Z standard, and I'm going to press enter. Oh my, can't see very much from all the way down there. It's probably not a very good graph or very good image. We can see our absolute value, but it's probably not the best. So I would probably recommend that you adjust the window by, well, we do want our x values to be going to -10. That's probably a really good thing. But the problem was our y values. We don't need our y maximum to be 10 necessarily, but our y minimum might need to be adjusted. So I'm going to change that to -20. And let's see what happens when I change. That's a lot nicer. We can see our absolute value. It's a very stretched out absolute value graph, but we can definitely see that. Okay, so like this is what our graph looks like. And it's saying for number 4, find the requested information about the graph. So we want to find the domain, and looking at this graph, we can see that it is pointing down. And that makes sense because our A value is negative. So our domain is still going to be all real numbers, but that means that our end behavior is going to be a down-down situation. So that is as x approaches -infinity, g of x, which is what this is called, will be approaching -infinity. And as x, positive infinity, and as x approaches -infinity, g of x is going to approach -infinity. Our range, well, our range value is based on our vertex, and our vertex, that's located at -4, -9. So the piece that we're most interested in is the y part of our vertex, and that's -9, and because the graph is pointing down, that means our y values are going to be less than or equal to -9. Or our minimum value is -infinity going all the way up to -9. And so the whole point of the graphing calculator is to give you a visual that might help you. And you would use this on like the SAT or some assessments whenever it comes to analysis. Otherwise, if we're having like quiz or tests on with actual graphing, I would prefer you not to use your graphing calculator, but I just wanted to show you that this is a resource for you as you are learning. All right, that is the end of today's lesson. I hope you have a wonderful day, but if you find that you have any questions, please feel free to email me, and I hope to see you soon.